Hey, this is Stephen Mossbrecher
and Anthony Nguyen.
And today I'm going to be talking about the winder and spooler assembly for our 106 project at San Jose State University. So the winder and spooler are for a machine known as the multi-extruder. The multi-extruder is a 3D printer filament maker. And how a 3D printer filament maker works is you put in plastic pellets at the top, which are made out of various different types of thermoplastics. It is then compressed and squeezed towards the bottom of a heated barrel to where the pellets melt, and then it's pressed through a die that turns these separate pellets, plastic pellets, that are like tiny little BBs, and it forms it into a continuous solid plastic wire with very good consistency on diameter. And the reason why you would want to make this plastic wire, it is known as filament. And the filament is used for most consumer grade 3D printers at home to make various different objects, like the winder, and the spooler assembly itself is also 3D printed out of material you would make on the multi-extruder. So the reason why you would need a winder and spooler assembly on the multi-extruder is to load filament onto the spool. Most 3D printers use filament that comes off of a spool. That way you could have a lot of weight in a small amount of volume, so you could print a lot of things with it, yet it's very easy to store. So what happens is, as the filament comes out of the multi-extruder, it needs to be wrapped as tightly as possible onto the spool so that you get as much weight out of the small amount of volume that you have for storage. So most spools hold 1 kilogram, so we need to wind 1 kilogram of plastic onto this spool as tightly as possible in order to get the maximum amount of storage space, so you could get as much filament into a small space as possible. So what we're going to be talking about is how these two are made, how they work, and also we're going to show you the wiring to the Arduino, the code on the laptop, and also a forced run and then a natural run over time. So how this guy works is that over one rotation of this spool, the winder has to indent 1.75 millimeters, which is the diameter of the filament that we are extruding. And the way it does that is with a Hall effect sensor, which is an input sensor, and then we have an output here as a servo motor on the winder. So let's go ahead and pull the winder closer, and we're going to go ahead and talk about how this is put together, and also it will give you a little bit of an insight on its operation. So here at the end we have a servo motor, which is known as a special type of servo motor known as a sail winch servo motor, and what that will allow you to do is get multiple turns out of the servo instead of a 180-degree rotation, which is half a turn. So here it says 4 turns. In actuality, it's 4 turns one direction and 4 turns the other direction for a total of 8 turns. So this servo will do 8 turns compared to a regular servo that will only do half a turn. It is glued. It is glued and bolted down to a 16-tooth GT2 pulley, and this pulley is, as you can see, there is a GT2 belt which is 6¼ millimeter wide, is attached to around this pulley, goes down across the winder module itself, and goes around a free spinning idler pulley that is bolted to the 3D printed frame. This is 3D printed out of PLA material, a very similar material that you would actually make filament for on this machine itself. Obviously, this is just 2 modules. The whole machine is not shown. So how this guy operates is, when I give a signal off the Arduino, which we'll go over later, this pulley, the servo will turn this pulley, and this particular carriage will go back and forth. And this carriage goes back and forth because it is sitting on a steel chromed rod, hardened rod, and it has a small polymer bushing on the inside to reduce friction and constrain the carriage to only go back and forth linearly, and it's also very, very quiet in operation. Then I'll show you where the signal comes from by popping off the camera here and moving the tripod out of the way. So the signal comes from the side of the spooler module. So here is a detailed look at the spooler module. It has 2 arms, 2 upright arms. This arm on the left hand side has a bearing inside with this cone that holds the threaded rod up, and on the inside we have a driven cone and a drive cone, and these are just two tapered cones that adapt to the hole that is going through the spool. And then these two cones have a nut inside, and you tighten them tight, and then this piece is this cone, the drive cone, is pressed onto a DC geared just regular DC motor, and this goes from about 10,000 RPM down to 5 RPM. So this is a very high torque motor, and because there's going to be a large load on this spool. And the sensor that we are working with here is a Hall effect sensor, which you can see here. Hall effect sensor is a sensor used to detect change in magnetic field. So we have down here, we have a magnet here that, as this magnet comes around, goes right underneath this Hall effect sensor, and the Hall effect sensor will detect this change in magnetic field and send a signal to the Arduino that we need to do something with the winder. So let's go ahead and talk about the electrical here. The winder module itself has the servo motor on it. The servo motor takes power, ground, and a PWM signal, which is a pseudo analog signal from the Arduino from pin number 9. As you can see there with the purple wire, comes off pin number 9. Then for the digital Hall effect, this is a digital sensor. So we have power, ground, and brown is signal. The signal goes into pin number 2, as you can see there with the brown. And pin number 2 is attached to an interrupt on the computer code, which we are going to go into right now as I plug back in the Arduino, plug back in the camera, and we're going to drop it down and look at the code here. So here is the code, and I'll show you guys from the start kind of how it's put together. So at the start here we see that I attached the servo library, and we have a starting position of 60. The starting position of 60 indents the rack all the way to the left hand side, and then we have a maximum of 122 degrees for it to hit the right hand side, and then also obviously the minimum is 61. So our degree of freedom here is about 61 degrees to go back and forth on this particular servo. And the whole travel of this rail is 107.2 millimeters, which means that every 1 degree on the program will indent us 1.75 millimeters, which turns out to actually be the diameter of our filament. So every time the spool makes one continuous rotation, we are going to have to indent the servo 1 degree, which will move the rack or the carriage 1.75 millimeters. So here we have indent, which is basically a method that I attach to the interrupt. So interrupt's attached to interrupt number 0, which goes to pin number 2, and whenever an interrupt is found, it calls the indent method. And the interrupt is triggered on a falling, which means that it's from a high to low signal. So it goes from 1 to 0. The Hall effect itself is a IC setup that whenever there is no magnetic field detected, it is a 1 or a high or 5 volts. And when there is a magnetic field detected, it goes to a 0, a low, or 0 volts. So whenever we go from 1 or 5 volts to 0 volts, it will call our method. And then I have the serial monitor begin, and at the beginning in my setup method, I want it to go to the home position, and I'm going to wait 5 seconds for it to get there. So now inside the indent function, basically what this says is that it will go from one side to the other whenever it detects a change in magnetic field. So what I'm going to do is I'm going to show you guys this in operation. Anthony is going to go to the other side with the magnet, and he's going to manually trigger the sensor, and we'll watch it move. So as you can see, the red light shows up whenever it sees the magnet that Anthony has in his hand, manually pressing behind the Hall effect sensor. And down here you can see that the rack is indenting. Now the reason why we are doing this is that the RPM is so low on the spool, 5 RPM, that this is very hard to notice any sort of movement. If you do the math on that, every 12 seconds this particular rack has to move 1 degree, or the servo has to move 1 degree. So every 12 seconds it's only going to move 1.75 millimeter. Now because Anthony is driving this system, you could see it a lot faster. And I'll have Anthony continue, and we'll go back over to the computer, and you'll see that here we have the serial monitor, and we can see the code displaying a serial debug line showing our indent from 66 back up to 121 back to 61, and you could see it slightly moving there. So while I set this back up, we're going to go ahead and start the motor itself. I'm going to go down and plug it in. So now you can hear the motor on the spooler module turn, and you'll also notice every 12 seconds you'll see the light up on the Hall effect sensor, and you'll see somewhat of a little bit of movement out of the rack every 12 seconds. And it's very, very hard to see, but it's actually moving. So that's pretty much it for these two modules and our 106 project. Me and Anthony thank you guys for watching, and we really appreciate your view. Thanks for watching. Take it easy.